Good morning, everyone, and happy Friday. We are going to be looking at Lesson 64 together today, so if you want to go ahead and open up your textbooks to Lesson 64, you can find it on page 260. We're going to cover a couple of different concepts today. The first one being we're going to talk about what a domain is, and then we're going to be talking about what the additive property of inequality is and how we can use that to solve inequalities. So I'm going to start off with a little example. I'm going to just grab another sheet of paper here and use that just to kind of give you a few things. You don't have to write any of this down right now. 1 minute here. Okay, I think I'm right here. There we go. Okay. So let's go ahead and, yeah, perfect. Okay, let's use this example for just a minute. Okay, so let's say that I have 25 cents and I'm going to go to the store and I'm going to buy eggs. And when I get there, I realize that each little egg is 10 cents each. Okay, so in other words, the total cost of one egg, we're going to represent it with an expression that looks like this. So the total cost of one egg, we would say it's 10 cents times the number of eggs that I buy, cents. That's how you figure out how much you're going to spend on your eggs, right? Now, sometimes we can use something as simple as 10x. Okay, so 10, where x represents the number of eggs. Okay, the variable doesn't really matter. In this case, we're going to leave it as capital N, little e, which indicates the number of eggs purchased. So I have to ask myself, well, with my 25 cents, how many eggs could I actually buy? Well, when I get there, I have three choices. I can either buy 0 eggs, not spend my money on eggs at all, or I could buy 1 egg, right? And in this case, let's go back over to the 0 eggs. If I wanted to take the number of eggs and put it into my little equation that we established over here, I would just say 10 times 0, and I'm not going to spend any money, right? 0 cents. If I buy 1 egg and I put that into my little expression, is 10 cents times 1 egg, obviously, is 10 cents. Letter C, I could buy up to 2 eggs. Using 10 times the number of eggs would be 10 times 2, and I've spent 20 cents. Okay, could I buy 3 eggs? No, I couldn't, right? Because number one, I don't have enough money. So I can't buy 3 eggs. That wouldn't work. How about 2.5 eggs? I have enough money to buy 2.5 eggs, but that's not realistic, is it? Obviously, unless it's hard boiled and you could cut it in half, which still wouldn't be appropriate in the grocery store. So I can't even buy 2.5 eggs. So my choices are only 0 eggs, 1 egg, or 2 eggs. Those are the choices that I have when I get to the store with my 25 cents. So in this case, what you see is that the variable that we have selected, either 0, 1, or 2, to be substituted, the numbers that could be substituted in for that variable is restricted, right? It can only be 0, 1, or 2. We call this restriction something known as the domain. And we're going to go into your packet and we're going to put a little definition in up here, the set of all possible input values. Often they're the x values, but you know sometimes we do see other variables just like you did with the number of eggs. But it's in a function, the set of all possible input values, often the x values, in a function is called the domain. Okay, the domain is also known as the independent variable. Remember, early on in the year, we talked about what an independent variable is. When you have that function machine, and you don't have to draw this out. In fact, I'm going to erase it in just a minute. But just to kind of jog your memories, whoops. Remember that little function machine I used to try and draw? Not so much the artist here today. But the number that goes in there that's going to represent, say we have 2 plus x equals 5. And I'm going to choose 3 to go in for x. So what's going in there is this x value goes into that function machine, right? 2 plus x is living in here. If I choose to use 2 to go in there, it's going to spit out an a y value, right? But y is dependent upon what I put in for x. X is known as the independent variable. It's the variable that I can choose. It doesn't have any bearing on what another variable is going to do. I get to choose x. It doesn't matter. So it works independently, but y that comes out is dependent upon what we put in for x. Okay, so the domain is also known as your independent variables for your problems that you're solving. Okay, but we call this restriction that we talked about in the egg example as the domain. Okay, so the domain, going back down to my little notes down here, in the case of these eggs, let's see how would we represent this. So every set and every inequality has this domain. We use the symbol D to represent it, and we specify our eggs in this case. Excuse me. The domain in my eggs includes the set of 0, 1, or 2. Okay, we can also say that domain includes all of the real, not all of the real numbers, but it includes real numbers, right? 0, 1, and 2 are from the real number families. Remember all our number families? So 0, 1, and 2, we've been practicing those particular sets for a little bit now. So 0, 1, and 2 come from all of the real numbers, right? So it's in that set. And also, the domain includes positive integers. Now, this is a good spot for me just to stop and explain the definition of an integer again. Remember that an integer includes I want to make sure I say it the right way here. I can't find it. But anyway, I know that all integers, and I want you to just kind of bank this in your mind, or you can jot this down. Integers includes all the whole numbers, their opposites, and 0. Okay, but nothing in between. So remember, integers are whole numbers, they're opposites. So in other words, all the negative numbers, and it also includes 0. Okay, so keep that in mind. So when we're graphing in a little bit, when we're graphing positive integers, it's going to look different than when we're graphing real numbers or rational numbers. Okay, because remember, fractions are not part of the integers. Okay, so just keep that in mind. So we're going to be seeing how we graph these differently. Okay, so let's move into the first example. I'm going to just do this one for you, and then I'm going to have you guys build a few into your notes. But let's look at this one. Let's say we're supposed to graph x is greater than 2. And we're told that the domain will include the set of all real numbers. Okay, so they're going to give you that. They want you to graph this on a number line. So we'll go ahead and get a number line on here. So we're graphing x is greater than 2, but we're restricting the numbers that are going to be selected for x to all real numbers. Okay, and those are graphs that we've already been practicing if you think about it. So if x is greater than 2, it does not include 2, so it would begin here at 3. And it will include all the real numbers greater than 3. We have our open circle. Okay, that's not tough. We've already been working on those kinds of problems. Let me add another sheet of paper here. Let's look at another example. Example 2. Let's say we are asked to graph x is not greater than or equal to 3. So here's a negated inequality. And the domain is restricted to integers. Remember, integers are all the whole numbers and their opposites and 0, nothing in between. Okay, so when we graph this, first of all, let's write the negated inequality here. If x is not greater than or equal to 3, well, then that must mean that x is less than 3. So to graph this, I'll just put -2 down here. -1, 0, 1, 2, 3, 4, 5. We'll just go since my number line can handle all those numbers. So x is less than 3. So it doesn't include 3. Now be careful, because here's where I want you to think with me for a minute. Integers, again, all the whole numbers and their opposites and 0, but nothing in between. So I can't graph it the way we graphed up here with a continuous line, including all the real numbers, because integers are restricted to all the whole numbers, positive and negative, and their opposites, so negative and 0. So I can't graph anything in between. So I'm just going to graph each one of those integers. However, since it's continuous flowing in the negative direction, it's all the numbers, all the integers, all integers less than 3, we only bold in your little arrowhead over there. That's the indicator that includes all those integers heading in that direction. All right, so in your notes, let's go up here. I'm going to go back up here. I'm going to have you guys put an example right here. So just call it example 1 right here. For you, it'll be example 1. And write down that we are going to graph x is greater than or equal to -1. And the domain here is restricted to the set of reals. Okay, so this means the reals, it includes all those number families on that table that we had. Remember that one we colored in early in the year? And also you can find it back in one of our lessons up here, right here, this table right here that shows you. So this is including all real numbers, which means it's including every single one of those numbers. Okay, so let's go back down to this example. All right, so we're going to graph x is greater than or equal to -1, and the domain is restricted to all real numbers. So put your number line here. I'm going to go ahead and start like down at -3. We'll start there. Okay, so now these are not integers, so we don't have to do just the dots on top of each one of those numbers. It's going to include all the numbers even in between on your graph, on your number line. So x is greater than or equal to -1, so it includes -1, and it goes on and on and on, includes all the real numbers. So we don't worry about this. We can go ahead and fill in that line that you guys are used to doing because it will include all of those. Now let's look at example 2. Whoops. Build this one in as well. We're going to put this one in your notes. Let's say we're asked to graph x is less than -1, and the domain is restricted to positive integers. All right, so we should already be thinking, what are positive integers? That would be anything above 0, whole numbers, right? Remember, integers themselves are all the whole numbers and their opposites, which are the negatives, and 0. But these are positive integers, so this can be 1, 2, 3, 4, and so on, but nothing in between. So let's see if we can graph this thing. Positive integers. I'm going to start my number line at -4. I want you to do the same thing because I want your number line to reveal that it's not going to include those negative numbers. Let's draw this a little bit further out. So let's look at this. So x is less than -1. Oh my goodness, now wait a minute. So if x is less than -1, it doesn't include -1, but it would include all of these guys, right? However, we're told that the domain is restricted to positive integers. So this doesn't actually help us graph any positive integers. So do you remember what they call this? There were 2 names for this: the null or empty set. So we can't even graph that based on the domain and its restrictions. And remember, they have a symbol that looks like this. So this would be the null or empty set. We cannot graph that. All right, let's try another one. You can put this one in your notes as well. Hopefully you didn't draw as big as I did. Let me add another page here. But you can put this on your notes still. I just can't fit it because I drew a little bit too big. Okay, so example 3. Let's see here. We're going to graph x is greater than or equal to -5, where the domain is restricted to the set of, oh, here we go again, positive integers. Now let's see, maybe we can actually get these on a graph. But keep in mind, again, they're integers and only the positive integers, which means it could be greater than 0, but we have to decide where we're going to be starting here. Now, x is greater than or equal to -5. Let's get this number line in, and I want you to start it at -5. Some of you like to do your graphs with only 3 numbers on it. I want to start seeing your graphs having more numbers on it. Okay, so we have x is greater than or equal to -5. So that means it can include -5, right? And all of these. However, it's positive integers. So actually, we can't graph anything below 1, not even 0, because it wants to be positive integers. So we are going to actually, and I'm going to make my graph just a smidgen bigger here. I'm going to go up to 4. So we can see a little bit more variety being graphed. Okay, so the positive integers that are greater than or equal to -5 would only be 1, 2, 3, and 4. And actually, we're going to color in and bold that arrowhead because it's all the positive integers greater than -5. Okay, but nothing in between, remember, because they're integers. And what are integers? Integers are all the whole numbers and their opposites, which means negative numbers, as well as 0. Okay, so that's a little bit about graphing using a domain. So you have to understand the domain restricts. It will tell you which, on the number line, which numbers we're actually looking to graph. Okay, so pay attention to what the domain is because that is a restricted independent variable. All right, let's look at the next section here. We have our addition property of inequality over here. We've been looking actually at already. We've been talking about, I want to go into our book here on the page where we talk about this, is on page 262. And page 262 shows the property listed there. Let me get there. Here we go. If you want to look there with me, up in the box up at the top, it states the additive property of equality. And we have used this many times to solve algebra problems. Here's what it says, basically. The additive property of equality slightly different than the additive property of inequality, but used the same way. But here's what we have been doing. Let's say that if A, B, and C are all real numbers, or any real numbers, and we say that A is equal to B, then if I add C to either one of these variables here, whoa, gracious day, yay, yay. Then they would still be equal to each other. I mean, you can test this. Let's just say that A happens to be, we'll set a value there so we can see it. Let's say that A is 3 and B is 3 because they're equal to each other, right? So if I put a 3 here, and let's say I add C to it, and I'll just make up a variable. Let's say it's going to be 5. I add 5 to that. 8 is equal to 8, right? So that additive property of equality, that's what we're actually using when we're moving our terms around in our algebra problems. For example, if we had x plus 4 equals 8, the additive property of equality, now I'm going to subtract 4, but it's really like adding a negative number. So remember, whenever you're thinking about moving terms, we're adding a positive or a negative number. We also say if we're adding a negative number, we're subtracting it, right? But the point is, I can balance my equation by doing the same thing to either side. Okay, so in doing this, it keeps my equation equal, balanced on both sides, as long as I do the same thing to both sides. Like this. I did the same thing to both sides. Keeps my equation in balance. Okay, so we've been using that to help us solve our algebra problems. So utilizing this property is when we do this. Okay, now let's talk about what the additive property of inequality is. Additive property of inequality is much the same way. The difference is we deal with inequalities. So think about what an inequality is versus an equality. Well, an equality is when we use an equal sign. An inequality is when we use a greater than, less than, or greater than or equal to, or less than or equal to sign. So for example, the additive property of inequality says that if we have A, B, and C, and they are any real numbers, and we say that A is greater than B, then if I add C to either one of those variables, the inequality sign remains true. So let's test this. Let's say I'm going to choose 5 for A and 4 for B, because it says that A is greater than B. So whatever I choose there has to state numbers that reflect that A is greater than B. So let's plug those in. So I'll put a 5 here for A and a 4 here for B. And let's say that we choose C is going to be 2. So if I add 2 to both of these, I'm going to end up with 7 and 6. So you see how this additive property of inequality works. It says that if I choose real numbers for A, B, and C, and I say that A is greater than B, I choose the numbers that A are greater than B, then this holds true. That if I add the same number to A and to B, the inequality statement remains true. So let's graph some of these. I'm going to have you put these in your notes also. So go back up here. I ran out of room up here, so I'm going to add another sheet here. But you're in your notes, okay? And hopefully you wrote small enough. If you didn't, you know what? You can write right up here. That's what we'll do. Let's handle this right up here. Addition property of inequality. We're going to put an example here. So be example 1 for this section. Let's say we're given this problem. X plus 2 is less than 0. Now you know where we are. I'm going to make this a little bit bigger. X plus 2 is less than 0. And let's say that the domain is restricted to all reals, which basically isn't a restriction at all, is it? But it is a restriction because it helps us know how to graph this and what numbers it can include. So we're going to solve this inequality by subtracting 2 from both sides. You end up with x is less than negative 2. Okay, so we're stating that negative 2, anything less than negative 2 will satisfy that inequality. So let's graph it. I'm going to start at negative 3, negative 2, negative 1, 0, and 1. I'll just put as many as I can fit on there. Okay, so if x is less than negative 2, it's not going to include negative 2, so we're going to put an open circle here, but it includes all real numbers less than negative 2. So we're going to bold that in right there. Okay. The next one, example 2, you're going to put right below there. And we have x minus 3 is less than, oh, sorry, not less than, greater than or equal to negative 5. And the domain is restricted to the set of integers. Now remember, integers are all the whole numbers and their opposites, which would be all the negative numbers, and 0. Okay, that's really important to know. They're not asking for positive integers here or negative integers. They're asking for all integers. So whatever we end up with as our solution here, we have to be careful how we graph this. So let's add 3 to both sides. We end up with x is greater than or equal to negative 2. Let's do our little graph over here. Oh, mine's a little crooked. I'm going to make it straight. And I'm going to start at negative 2, negative 1, 0, 1, and we'll put a 2 on there. Okay, so let's graph this. So x is greater than or equal to negative 2. So we know it can include negative 2. But remember, we're going to only put dots. Now, it's a closed-in circle. It includes all the integers that are greater than or equal to negative 2. So it includes negative 2, it includes negative 1, 0, 1, 2, and so on. So we have to color in that arrowhead to indicate that it includes all the integers heading on in that direction to the right on our number line. Okay, but remember, it does not include any of the numbers in between because integers are not those numbers. Okay, and that sums up the lesson. Let's go ahead and look at your practice set here. Letter A in your book says that we are going to graph on a number line that x is less than or equal to negative 2, and the domain is restricted to the set of all positive integers. If you want to try these and pause the video and come on back, feel free to do that. But we're going to go ahead and work these through. So x is, not less than. So we've got to put a line through that. I'm going to go ahead and write these out. B is x is not less than or equal to 4. And the domain includes the set of all real numbers. C, x minus 5. We have some inequalities here that we have to solve for. X is not less than 0. And the domain is restricted to the set of all integers. And then finally D, x plus 2 is less than 5, and that domain is restricted to the set of all integers. All right, so let's go back over here. So if x is not less than or equal to negative 2, then that means that, I'm going to write this one in green, that means that x has to be greater than negative 2. All right, so we're going to graph this. It's positive integers only, but I'm going to start at negative 2 since that is part of our inequality. And we're going to graph positive integers only. Okay, so any x values that can be graphed on there have to be not only greater than negative 2, but only the positive numbers that are greater than negative 2. So that would include 1 and 2, and all the others in that direction that look like that. 3, 4, 5, okay? Make sure you're not drawing your actual line because it does not include any of the numbers in between 1 and 2, or in between 2 and 3, and so on. All right, let's look at B. So B says x is not less than or equal than 4, so that means that x has to be greater than 4. So let's get this one graphed, and I'm going to put my graph, I'll just start at 1, just to get a few numbers on my number line. And the domain is to include all real numbers. Okay, so we're just graphing this one like a regular little graph like we've been doing. We've had lots of practice on this. It does not include 4, so we have an open circle. But since it includes all the reals, that means it includes all whole numbers and all numbers in between, rational and irrational. Letter C, x is not greater than, we have an inequality to solve here. All right, so we're going to add 5 to both sides here. And then we're going to end up with x is not less than 5. So we're going to turn this around. So if x is not less than 5, actually, the negated inequality would be written as x must be greater than or equal to 5 then. So here's what we want to pay attention to. We also see that the domain includes all integers. And it happens to be that they're going to end up being positive because 5 is positive here. So we'll just graph a few numbers on here. We'll go 2, 3, 4, 5, and 6. And we'll show here on the number line. So if x is greater than or equal to 5, it will include 5 integers, so no numbers in between, but in that direction forever and ever. Okay, letter D. Let's solve this thing. So we have minus 2 on both sides. Handle it just like a regular equation. X is less than 3. And our domain is restricted to all integers. So all integers that are less than 3. So we'll put a few numbers on our number line. Please build a few in there. We can maybe start at 4, 3, 2, 1, 0, -1, and -2. That's a nice variety to show this. Integers will include the whole numbers and their opposites and 0, any of those that are less than 3. So it does not include 3, but it does include 2, 1, 0, -1, -2, and so on. So we have to bold our little arrowhead over here. Okay, and that is how you do those graphs. I hope that was helpful. I hope you guys have a great weekend and enjoy your Monday off. I will see you all on Tuesday. Please make sure that this lesson is completed when you return. All right, all, have a great day. Talk to you later.